Okay, today we're going to talk about forces between atoms and molecules. These forces, there are two types. One is called intermolecular forces. Those are the forces that are between. So inter means between, like an intermission when you are in between acts of the play or the movie or whatever you're at. So inter means between, and that's exactly what intermolecular forces are, the forces between molecules. As you can see, I drew a nice little picture here of water. This is one water molecule right here, the H2O. And then we have partially positive and partially negative because it is polar. So we have a pole going towards that oxygen, pulling the electrons more than the hydrogens. The other water molecule then interacts with that water molecule. So we have two separate molecules. And in between them, so in between this water molecule and this water molecule, we have an interaction, and this is designated by this dotted line. It's called an intermolecular force. Now, what does this matter to us? It basically tells us what kind of phase it might be in. The phase, if we have really weak intermolecular forces, or intermolecular forces are really weak between the molecules, we most likely have a gas because they're not held very tightly. If they're very, very close and strong, that means we probably have a solid. It also determines our melting point and our boiling point, because if the forces are really, really strong holding these molecules together, it will be much harder to melt or boil that substance, so the melting point and boiling points will be higher. If they are weaker, obviously it's much easier to take those substances apart, and that melting and boiling point would be very low. As a result of that, vapor pressure means how much vapor is in there, how much vapor is available. That vapor is created when what? It falls apart from boiling. It comes apart into vapors. And that vapor pressure will build if it's, again, a weak substance, weak intermolecular forces, then you'll have a high vapor pressure, but a low boiling point because it happens very quickly, and vice versa. The next kind of force is the intramolecular forces, which are the actual stronger forces here. Why? Because intra means within. Within the molecule means the actual bonds. So when we say intermolecular, we mean the bonds. So when we have a water molecule, like I've shown you before, we only have to have one here to show this, whereas intermolecular, we had to have the two molecules to see that they were interacting with each other. The intra is the HO bond, and then this HO bond is also an intermolecular force. They are way, about 100 times stronger than the intermolecular forces themselves. Now, what we need to do in order to determine questions like, hey, who has the highest melting point? Who has the lowest boiling point? Whatever questions we're going to ask are based on what the force is. We have a hierarchy. Hierarchy means we put them in order, and they are going from strongest to weakest. So ionic over here is the strongest, and London is the weakest, or London dispersion. So in order to remember this, I just put it into an acronym. I call it I hate dirty laundry, which I do. So I hate dirty laundry. I stands for ionic. To be an ionic, you have to see a metal, and the metal is always first, and then a non-metal. Game over. If, though, it is not that, you go on and you figure out, maybe I have a hydrogen bonding occurring. Hydrogen bonding is exactly like it sounds to begin, at least. It has to have a hydrogen. That hydrogen is going to be fun. I said hydrogen bonding is fun, kind of like fun, but fun. Much easier to remember that H bonded to an F directly, H bonded to an O, or H bonded to an N. Those are what we call hydrogen bonding. If the H is not directly to F, O, or N, then it is not hydrogen bonding. Sometimes you'll have to draw out a structure to see if that is true. These are the strongest kind of dipoles, which is our next type in a second. So really, hydrogen bonding and our next weakest is dipole-dipole are really the same thing. It's just hydrogen bonding is given a special name because it is very special. By the way, hydrogen bonding, the strongest of them is the HF because fluorine has the highest electronegativity. Nitrogen has a little lower, but they're very, very similar, but it goes from strongest to weakest in the order that I have it written. Okay, moving on to the I hate dirty. The dirty part is the dipole-dipole. Dipole-dipole can sometimes be challenging, but dipole means two poles. And what that means is we're going to end up with a polar molecule, or something that is not symmetric. It is poling one way more than the other. We have something that's more electronegative overall. And most of the time, like I said, you're going to have to draw those out. So the laundry part stands for London dispersion. I always like London dispersion being the weakest because I always think of London bridges falling down. That's pretty weak. In London dispersion, we have a couple categories. All the non-polar. So why we have to distinguish when we draw substances out is if it's a dipole-dipole, which is polar, or if it's non-polar, then it's going to be London dispersion in the weakest. Non-polar means everything is symmetric and cancels each other out. It's like playing tug of war with the same person. You're not going to go anywhere. No pole. Your Hoberfinkels, or your diatomics, or your Brinkelhoffs, if you're in Miss Ward's class, Hoberfinkels. And then your noble gases will also have London dispersion. So those are your weakest forces. Now the questions that you'll get a lot are, what is the predominant force? The predominant force means what is the strongest force available? Because really, once you have hydrogen bonding, that is actually hydrogen bonding is the predominant force. You also have dipole-dipole because it is really the same thing. And then you also have London dispersion. So every molecule actually does have London dispersion, but we are going to go for what is the most predominant force, the strongest one reacting. So we look at the substance, and basically what I would do is go through the list. I hate dirty laundry. So ionic, is that a metal in the first element here in NH3? N is not a metal, so it's not ionic, so go on. Hydrogen bonding. Is there a hydrogen? Well, yes, there is. Is it hydrogen bonded to a nitrogen? Yeah, that's all that can happen here. So H to the N is hydrogen bonding. By the way, we will go ahead and abbreviate it, HB. Hydrogen bonding will be your most predominant force, even though we actually do have dipole-dipole and London dispersion, but we're only asking for the predominant. Next one, number 2. Lithium fluoride, Li. Go through the hierarchy again. I hate dirty laundry. I is ionic. Is the lithium a metal? Well, yes, it is. It's a metal. And then I have a non-metal. So guess what? Game over. It's ionic. That is the strongest. Of course, it will have the other types of bonding too. pH3. Now this one could be a little tougher. I look first though and I say, is it ionic? No, that is not a metal. Phosphorus is not. Is it hydrogen bonding? Well, I do have the hydrogen, but is that Pon? Is that an F, an O, or an N? No, that is not. So we must figure out, is it dipole-dipole or London dispersion? When we do this, we have to figure out if it's polar or not polar. In order to do that, we have to look on our periodic table and draw the shape. So phosphorus has 5 valence electrons. Each hydrogen brings 1, and there's 3 of them. So that is 8 total electrons around that molecule. So if I go out to the side real quickly, I put P in the center because it is a single atom. I put my hydrogens around it. I'm just distributing them. I have no idea what the shape is. And that already gives me 2, 4, 6. Each hydrogen's already happy, and that 8th pair is going to go on my phosphorus to make it happy with an octet. And that makes that trigonal pyramidal. It doesn't matter, but I want you to know that so that we are remembering that again. And trigonal pyramidal, because of this unshared pair, is polar. So we have a polar molecule, and polar means dipole-dipole. So we're going to look at number 4. Number 4, again, ionic first. Is that a metal? No, boron is not. Boron is a metalloid, kind of close, but not. Boron is not a metal. Is there a hydrogen involved? No, so it's not hydrogen bonding. So let's go ahead and draw it out again. Boron has 3 electrons. Whoops. Fluorine has 7 for each of those, times 3 is 21 plus 3 is 24. Now, if we draw this out, I already know the structure, so I'll kind of go with this. We are going to draw all those lovely unshared pairs to give the fluorine an octet on every one of them. So we're adding 2, 4, 6, and then we have the 8th one that was shared here already. 8 times 3 is 24. Remember, boron is an exception. So it does not need that 8th one there. So that is its structure, which makes it trigonal planar. And trigonal planar is that very bizarre one that we talked about, that because they all are in the same direction like that in a 360 same plane, it actually does cancel out, and it is non